This is problem 5-22, it's on page 209. A flat steel strip is used as a spring to maintain a force against part of a cabinet latch in a commercial printer as shown in figure P5-9. When the cabinet door is open, the spring is deflected by the latch pin by an amount Y1 equals 0.25 millimeters. The pin causes the deflection to increase to 0.4 millimeters when the door is closed. Specify a suitable material for the spring if it is made to the dimensions shown in the figure. So we're given the solution to 5-9, and what that really means is that we've got the mean stress, which was 386.2 megapascals, and we have the variation in the stress, the amplitude of variation of the stress. It was 89.2 megapascals. We're supposed to specify a steel, so we're supposed to find what steel will work here. Well, let's just go with cheap stuff. Let's go with something that's fairly weak. Let's try 1020 annealed. All I did was I looked in the back of the book at all the SAE steels, picked the one with the lowest yield and ultimate strength that I could find. In fact, I found that it had an ultimate strength of 393 megapascals and a yield strength of 296 megapascals. Now it has a lot of ductility. I think the ductility was 35% or something ridiculous. So it could stretch like crazy, which was really good because remember this spring is deflected pretty far. Most of the time we assume that the beams that we're designing don't deflect very far, but this is deflecting by 0.4 millimeters and the span's only 40, so it's deflecting, what is that, a hundredth of its length? That's a pretty big deflection for what we're doing. And so I thought, well, let's get something that has the highest ductility I could find. And so this was the weakest, but it was also the highest ductility. Let's see what happens. In order to get the strength of this thing, or see if this will work, we really need to check the safety factor, right? We want to calculate the safety factor because if the safety factor is greater than 1, then the steel we've chosen would work. So to calculate the safety factor, I'm going to need the actual endurance strength, so I better use the ultimate strength to get the endurance strength. And then from that I can get the actual or estimate of the actual endurance strength. So if you take SU, there's no curve for annealed to get SN. So what I did, I just went down to the lowest one, which was S forged. And so that was the best I could do because if you roll this, you're going to increase its strength, but this one's completely annealed. Okay, it's at the lowest strength it could be, so I just chose S forged, even though S forged has more to do with the surface roughness than anything else. But it was just the best estimate I could think of. So SN then came out to about 110 megapascals. Okay. So using 393 on the x-axis, going to the as forged curve gave me 110 megapascals for the endurance strength. Now to get the actual endurance strength, or at least an estimate of it, I need to modify it with a bunch of different factors. Okay, so I need reliability factors, type of stress factors, all those things. Sm prime then is Sn, 110 megapascals. We'll just we'll put in the factors as we go. So we need a material factor first, Cm. Well, this is steel, so it's 1.0. It's not cast iron. We need a type of stress factor. Well, if it's bending stress, then it's 1.0. If it's axial stress, it's 0.8. Well, this is bending stress, obviously. We're bending the spring quite a bit as a beam, so that's 1.0. How about the reliability factor? Well, I don't think I would want to open my cabinet door and it fail anytime soon, so I chose a 99.9% reliability, and that gives me a reliability factor of 0.75 or 75%. So this is a 99.9% reliability. Okay, that's just got that off the little table in the chapter. Okay, so that's that. What about the size factor? Well, unfortunately, the cross-section was a rectangular cross-section, and remember it was 0.6 millimeters high by 5 millimeters wide. And so what I need to do is get a size factor. So the size factor, well, it depends on the equivalent diameter. So I guess I need an equivalent diameter first. Okay, let's do that. So we'll start off with an equivalent diameter. And for a beam like this that's rectangular, it's 0.808 root HB, where H is the height of the beam cross-section and B is the base. So that's 0.808 multiplied by, well, the square root of 0.6 millimeters times 5 millimeters. Take the square root, we'll get a result in millimeters, which is good. It comes out to about 1.4 millimeters. Now, if you go and you look for what equation to use, your text says that if the size, the diameter, is less than 7.62 millimeters, then go ahead and use a size factor of 1.0. So that's what I did. So this tells us that the size factor is 1.0, and I don't have to worry about it. Okay? It's very thin, there's not much material here. So, plugging all this in, we'll get our modified endurance strength estimate, 82.5 megapascals. That's what we came here for. We got SN prime, finally, after all that work. All right, so 1020 annealed. Let me, I'll tell you what, I'll just keep working down here. I'll just get rid of this part. This was a 99% or 99.9% reliable. Okay, so let's use the Goodman criterion. It says that the stress concentration factor times the magnitude of the alternating stress over the actual endurance strength plus the average stress over the ultimate strength equals 1 over n. Rearranging this, we get that the design factor or safety factor is Sn prime Su divided by Su kt sigma A plus Sn prime sigma n. Plugging in all of our units, or all of our numbers, well, the units don't matter, right, because they're going to cancel. As long as everything's megapascals, it'll be okay. So 82.5 was the modified endurance strength. The ultimate strength was 393 megapascals. SU is 393. Stress concentration factor of 1, because there were no stress concentrations. If you remember from the figure, or if you go look at it, you'll see there's no holes or nicks in it or anything like that. So stress concentration factor should be 1. The alternating stress was calculated as 89.2 megapascals. We need to add Sn prime, 82.5 megapascals, multiplied by the average stress, 386.2 megapascals. Plug all this in your calculator, you get a grand total of 0.48. This is a problem. This design factor is less than 1. That means it will fail very quickly due to fatigue. With these stresses and these deflections, this material will not work. So what can we do? Well, we need a stronger material. Usually spring materials are very strong materials. They're not very weak materials. Things like music wire, for example, is a very strong material, and it can be used to make springs. So this 1020 is not going to work. Let's change it. So what I did is I went and I looked for material that was about 3 times the strength of this. And why did I choose 3? Well, I'm just kind of guessing. I mean, it looks like I need double the strength roughly. So I went ahead and made it 3 times because I didn't want to go through this again if I didn't have to. So I said, I'm just going to find a material that's about 3 times as strong. So I found that 4140 OQT 1100 had an ultimate strength of, is it not quite 3 times that, it's 1014 megapascals, before we had an ultimate strength of about 400, so about 2.5 times. And it has a yield strength of 903. And yet its ductility is still 18%, so it can bend quite a bit, which is nice. It's not going to just fracture from bending. So that 18% ductility is what sold me on it, because it's strong but yet still fairly flexible. And by the way, this was a hot rolled steel. Now, if I go and I look up about 1,000 megapascals to get the action, or to get the endurance strength, I'll find that I get about 225. Okay. Well, that's better. Now this is not as forged because this is a hot rolled steel, so now what I need to do, or what I did, was I went to the curve for hot rolled instead of for the curve for, as forged. So this is quite a bit more strength. This is a little more than twice the strength we had, well, even more. We had, what, 82? No, it was 110. So we got right at twice the endurance strength. Now to get the modified endurance strength, or the estimate of the actual endurance strength, plug in 225 here. Factors are all still the same because the size hasn't changed. And instead what we will get is about 169 megapascals. Now the Goodman criterion is still the same. All I really need to do is just get rid of that 82.5, which wasn't big enough, right? Because look, the ultimate strength, well, I got to change that too. That did change. Well, I guess what didn't change was the stress concentration factor and the amplitude and average stresses. Everything else did change. Okay. 169 megapascals for Sm prime. Ultimate strength, 1014. Ultimate strength, still 1014. And then finally Sm prime, 169. When you plug all of that into your calculator, what you'll find is that you get a design factor of 1.10. This is okay, this is a marginal design, but it's not the end of the world, it should work. Okay? If this is an airplane, it's probably not good enough. If this is a car, it's probably not good enough unless you're making really cheap cars. But for a cabinet door, this is 1 out of every 1,000 failing. I'm okay with that. Maybe these are cheap cabinets, I don't know. But we need to also check yielding. So let's get rid of this part since we don't really need any of it. Because I don't want these springs that are supposed to, help with the cabinet door somehow. I don't want them breaking due to yielding. They wouldn't, if they yield, well, it's, that's no good. If it yields from all this loading, then it will no longer serve as a spring. So let's find out. Well, the equation is as follows. That's an A, by the way, the alternating stress. We can rearrange this pretty easily to solve for n. It comes out this way. Okay. The stress concentration factor I'm still going to set to 1. The yield strength is 903 megapascals. And the amplitude of the alternating stress is 89.2 megapascals. The average stress is 386.2 megapascals. Sure enough, units cancel as they should. And so now I get about 1.9. Now, the factor or the thing that's going to make this fail first is the fatigue loading, the fluctuating load. Okay, the yield strength has a higher factor of safety, so that's not what would cause failure here. This design is not great, but it should work unless there's some stress concentration I've missed somewhere. You might want to look at a spring steel because there are other steels that are much stronger. They're intended for springs, and this material that I've chosen is not really a spring material. So if we could find a spring material, we could probably get this design factor up a little bit, which would be a good thing.